Okay, hello and welcome back. In this video, we're covering section 7.4 on factoring two special forms of trinomials and binomials. The first one will be the perfect square trinomial, and then the second will be the difference of two squares. So these are two patterns that we can recognize to help make factoring a bit easier. So let's look at the first one, the perfect square trinomial. We'll see the pattern and how we can utilize it. So we've actually seen this pattern before, but from the opposite perspective. In the previous chapter, we multiplied out something like a plus b squared, a squared factor. So we can write this as a plus b times a plus b, since it's being squared. And then if we FOIL this out, the first two terms multiplied would give us a squared. Second, the outer would be a times b, so plus a times b. The inner two would give us another a times b, and then the last would be b times b, or b squared. So combining these two middle like terms, we get a squared plus 2 times a times b plus b squared. So we said previously if we had something like a plus b squared, we can jump straight to the right side. So we'll work on going in the reverse direction. We'll start with something like this. We'll have to recognize that it's in this pattern. And then if it is, we'll be able to jump straight towards expressing it as a squared factor. So that's what they mean by a perfect square trinomial. Some trinomial that factors into a perfect square. And this also works if we had something like a minus b squared. In the same way, this would be a minus b times a minus b, which would give us a squared minus 2ab plus b squared. So we'll do the same. If we start with something on the right, we'll be able to jump to factoring it as what's on the left here. So that's what they have here in our box from the textbook. They just have it flipped. So if we have something like a squared plus 2ab plus b squared, can factor into a plus b, that whole quantity squared. And the same if we have a subtraction. So let's look at a few examples and I'll show how we can recognize that we have this particular pattern. So in the first example, we're given k squared plus 18k plus 81. So the first way to check for this is to look at the first and last terms to see if they are something squared. Like our first term we can write as k squared. And then that last term, 81, we'll have to recognize that this is 9 squared. 9 times 9 gives us 81. So what we're testing for is if this middle term is the result of taking 2 times k times 9. That would be our 2ab. If our a is k and our b is 9. So 2 times k times 9, 2k times 9 gives us 18k, which is that middle term. So this does fit that pattern, which means it should factor into k plus 9 squared. So it's a bit of a shortcut. We could still factor this as we've done previously. And I'll do that over here just to show. If we have k squared plus 18k plus 81. Previously we looked at factors of 81, so two things that multiply to 81 that will add up to the middle term of 18. And after playing around, you should get 9 and 9. 9 times 9 is 81, 9 plus 9 is 18. So we would write the two factors as k plus 9 times k plus 9. And since they're both the same number, we get repeated factor, which means that this can be written as k plus 9 squared. So we still get the same result. You can always just factor it as we've done before if you don't recognize this a squared plus 2ab plus b squared pattern. But if you do, then you can jump straight towards writing the factor. So let's look at a few more examples and see when this would apply and when we can tell that it will not apply. So from example 2, part A gives us c squared minus 16c plus 64. So our first term, c squared, that's c squared. And then the last term, 64, that looks like 8 squared. So what I'm checking is if I do 2 times c times 8, do I get negative 16c? If I do this, I get positive 16c. So I have to think, is there a way I could change my values in order to get a negative? If we replace this 8 with a negative 8, negative 8 squared is positive 64, so that will still work out. So then if I turn this into a negative, 2c times negative 8 will give us negative 16c, which is that middle term. So we just needed a negative. So that means that this should factor into c minus 8 squared. And we can always multiply this out just to check. This would give us c squared minus 8c minus 8c plus 64. And we can see that will give us our minus 16c in the middle. This was if we FOILed it as c minus 8 times c minus 8. So you can always do that to see if you have the correct result. All right, let's look at part B. B gives us 4t cubed plus 32t squared plus 64t. So the first step in factoring should always be just seeing if we can factor out some greatest common factor out of every term. It looks like in this case every term has a t, and every term is divisible by 4. So let's factor that out in front, and it will reduce everything that remains. If we take out 4t, there should be t squared left over from the first term. 32 divided by 4 is 8, and we take 1t out, so there'll be 1t left. 64 divided by 4 is 16, and we took the t out, so it'll just be 16. So now let's factor what's remaining inside these parentheses. So checking for our pattern, I see we have t squared, and then 16 is 4 squared. So I'll see if I do 2 times t times 4, does it equal 8t? Which it does. So that means inside those parentheses, it should factor into t plus 4 squared. And then we have the 4t out in front. For part C, we have 9w squared plus 12w plus 4. So first I'll see, can I factor anything out of every term? They don't all have w, and they're not all divisible by some number. So let's continue with it as it is. The first term, 9w squared, we can see that as 3w squared. That would give us 3 squared times w squared, 9w squared. And then that last term, we have 4. We can write that as 2 squared. So looking at that middle term of 12w, if I do 2 times 3w times 2, that's our 2ab. 3 times 2 is 6, 6 times 2 is 12, and then we have our w, so the pattern checks out. So that means we can write this as 3w plus 2 squared. Part D gives us 4c squared plus 20c plus 9. So I'll check first, can I factor something out of every term? It doesn't look like it. So let's look at that first term, 4c squared. We can write that as 2c, that whole thing squared. And then our last term, 9, we can write that as 3 squared. So I'll see if I do 2 times 2c times 3, do I get 20c? Well, this looks like this will give us 12c, which is not equal to 20c. So that means this can't be factored using this method. It is not a perfect square trinomial. So at this point, I would just factor this using a previous method. I'll use the AC method. So I'm going to multiply the A term and the C term. That's 4 and 9. So 4 times 9 is 36. So now we'll look for two factors that multiply to 36 that add up to our middle term of 20. So if you play around with some values, you should end up at 2 and 18. 18 times 2 is 36, and 18 plus 2 is 20. So then let's rewrite the middle term, 4c squared plus 2c plus 18c plus 9. Then we'll put these into two groups and factor by grouping. So 4c squared plus 2c in parentheses plus 18c plus 9. So in our first set, it looks like we can factor out 4 and 1c. We'll be left with, or no, sorry, we can't take a 4 out, but we can take a 2. So if we do 2c, 4 divided by 2 is 2. We took 1c, so there's 1 left. And then we took 2c out, so there should be just plus 1 here. We can check, that would give us 4c squared plus 2c. And then in the second set, they're both divisible by 9. So let's take a 9 out. Then we'll be left with 2c plus 1. So we can write our common factor, 2c plus 1. And then our second factor will be 2c plus 9. So this didn't factor into a perfect square where we end up with some squared factor, like 2c plus 1 squared. We have two different factors. So this pattern won't work every time. Sometimes you'll have examples that won't factor in this way. But if we can recognize this pattern, it makes the process a little bit shorter. So the second pattern we'll see is called a difference of squares. And we have seen this before already as well, from the opposite direction when we multiplied something like a plus b times a minus b. Foiling this out, we'll get a squared minus a times b. plus a times b minus b squared. Those two middle terms cancel out because one is positive, one's negative, and this ends up just giving us a squared minus b squared. So that means if we can recognize this, if we have something that is a difference of two squares, two things that are squared, a squared minus b squared, we can jump straight to factoring it as a plus b times a minus b. Let's go through a few examples. Part A, we have c squared minus 36. Can we write this as the difference of two squared things? C squared, that one's easy, that's c squared. And then 36, that is 6 times 6. So this can be written as c squared minus 6 squared. So that's a difference of two squares, which means we can factor it as c plus 6 times c minus 6. Part B, we have 49x squared minus 25y squared. So we have variables on both of our terms. So we just need to see, we can see that we have x squared and y squared. So the question is, are the numbers in front of these also something squared? The first term is 49, which is 7 times 7. So this can be written as 7x squared. And then our second term is 25y squared. And 25 is 5 times 5. So this can be written as 5y squared. So we have a difference of two squares. It'll factor into 7x plus 5y times 7x minus 5y. So it still works if we have some number as well as a variable squared. Part C, it looks like we have a fraction, so let's see if we can still express it as a difference of two squares. We're given t squared minus 4 over 9. So t squared, we can write as t squared. And then 4 over 9, it looks like we have a division of two squared terms. 4 is 2 times 2, and 9 is 3 times 3. So we can write this as 2 over 3 squared. If we were to multiply 2/3 times 2/3, we would get 4 over 9. Or we can apply the exponent to the top and bottom of the fraction. So we still have, even though we have a fraction, a difference of two squares. So this can be written as t plus 2/3 times t minus 2/3. And then let's look at part D. We're given k squared plus 81. So we do have two squared terms. We have k squared, and 81 is 9 squared. But this is a sum of two squares. So this pattern only works if we have a difference, if it's a squared minus b squared. So in this case, this is not a difference of squares. So we'd have to try to factor it some other way. In this case, we'll just have to call this prime. It's not factorable to two more simple factors. So the big caution here is that it only works with a minus if we have a difference of 2. We don't have a similar pattern for the sum of two squares. So let's look at a few slightly more advanced examples. In example 4, part A, we have 300p minus 3p cubed. So first I'll see, can I factor something out of both terms? They're both divisible by 3, and they both have a p term. So that would leave in parentheses, 300 divided by 3 is 100. And we factored out the p variable, so that won't have one. And then for the second term, we took the 3 out, we divided by 1p, so there should be 2 left over, 100 minus p squared. And then what we have remaining in those parentheses, 100 is 10 squared, and then p squared we can write as p squared. So we actually have a difference of squares remaining inside of the parentheses. So that means this will factor into 3p times 10 plus p times 10 minus p. Okay, part B. We're given 7w squared plus 28. So can I factor something out of both terms? It looks like they're both divisible by 7. We'd be left with w squared plus 4. And here it's tempting to do this as a difference of squares, w plus 2 times w minus 2. But we have a sum. So that's that same issue we saw before. It's not a difference of squares. So we'll have to stop here. We won't be able to factor this any further. Part C, we're given x to the 4th power minus 81. So the 81, that's definitely 9 squared. But x to the 4th power, it's a little bit tricky, but we can see this as x squared squared. If we were to apply that power raised to another power, they would multiply, and we would get our x to the 4th power. So that means this can factor into x squared plus 9 times x squared minus 9. And then notice here we actually get another difference of squares. The first one is a sum, so we can't factor that any farther. But we can write this as x squared minus 3 squared, difference of 2 squares. So that second set of parentheses will be able to split into 2 more factors, x plus 3 and x minus 3. So sometimes it's an iterative process, meaning we can keep going. Once we do some factoring, we can look at the result and see, can I factor it any farther? Can I apply some additional method or some other pattern in order to further factor what we have? Okay, so that will be it for this section. We saw these two special forms, the perfect square trinomial. That's if we had something like a squared plus 2ab plus b squared. It factored into a plus b squared. And then difference of squares, if we had something like a squared minus b squared, this will factor into a plus b times a minus b. So these are two useful patterns. I'd say particularly the difference of squares, that one comes up a lot. And if we can learn to recognize these, it can make factoring a bit more smooth. We'll be able to pick up on these patterns and jump straight to what it will factor into. Okay, that'll be it for this video, and I'll see you next time.